Hello everyone. Today we have Brandon, myself, Ryan, and Chika here to tell you about the product we developed, which is called the headset for aviation and life-saving operations. Now to begin, we're just going to recap a little bit about what our project mission was. And in our research, we noticed that there are numerous aircraft crashes that are caused by medical emergencies. So due to the nature of their occupation, pilots are actually susceptible to the conditions listed on this slide. And all of these conditions can have a seriously negative effect on the pilot's ability to operate the aircraft safely. So there's currently no way to monitor for these conditions while in flight. And if we look here, just by monitoring these 6 different medical parameters, we can actually get information about all these different medical conditions. And even so, we can have information from multiple sensors to give even more information and really help somebody determine if a health issue is present. So with this information, it is our main goal to develop a sensor suite that will monitor pilot health while in flight. And if their health reaches a critical state, the pilot or another crew member could notice the issue and act quickly to ensure the safety of everybody on board. To achieve this goal, the sensor suite that we constructed monitors these 6 health parameters that we mentioned on the previous slide in a non-invasive manner to help identify medical abnormalities.
As with other Capstone teams, we developed some metrics and specifications last semester to better help understand our product and how we'd like to go about accuracy and precision of results. Unfortunately, due to coronavirus, we weren't able to test all the things that we initially thought we would be able to last semester, but we did focus on the precision of the sensors compared to reputable sensors, which we're going to call the gold standard. And so in doing so, we chose 95% accuracy for the heart rate monitor, 90% for the pulse oximeter, 90% for perspiration, 90% for temperature, 80% for respiration, and 80% for the head motion monitor. And those rates are just based on the essential importance of the sensor and the medical trends that we'd like to evaluate. So obviously the heart rate monitor is essentially the central sensor, which is why its accuracy is essentially the most important.
So here we can see a schematic of the assembled H.A.L.O Mark I, our headset sensor suite, contained mostly within a clip on the headband. If we zoom into the headband, you'll notice 2 thermistors used for gathering data on body temperature, and following that is our heart rate and pulse oximeter hybrid sensor, which is designed to monitor the state of the pilot's cardiovascular system optically. A skin conductance sensor is used to quantitatively monitor whether or not an individual was sweating, and a triple-axis accelerometer was used to track head motion for signs of fatigue and other distress. A high-sensitivity microphone is used near the mouth, mounted on the headset microphone, and the sound waveforms were used to monitor respiratory rates. In regards to the heart rate monitor and pulse oximeter hybrid sensor, the target conditions to be monitored by this output signal are heart arrhythmias, hypoxia, hypertension related to high-stress environments, or any irregular heartbeat. In particular, this sensor targets the frequency related to the heartbeat as a function of voltage over time, where voltage is inversely proportional to the measured intensity value. The hemoglobin contained in the blood erythrocytes is the absorbing species of interest, and as the compliance in the arteries allows for a larger volume of blood to be held during systole, more light will be absorbed during a contraction. This can be seen as pulses in the graph data seen in a couple of slides as a decrease in reflected intensity. 430 nanometer light was chosen here as this is a peak in the molar extinction coefficient of hemoglobin, and in a similar vein, pulse oximetry is calculated as a ratio of absorbances between oxygenated and deoxygenated blood, where oxygenated blood has a higher extinction coefficient at 625 nanometers and deoxygenated blood has a lower extinction coefficient at 970 nanometers. The ratio is given by the equation seen on the lower left side of the screen, where a ratio of 1 represents a pulse ox of 85%, a ratio of 0.4 represents a pulse ox of 100%, and a ratio of 3.4 represents a pulse ox of 0%. The main challenge here is the very small amplitude of the heart rate signal in comparison to other ambient frequencies, which will have to be accounted for in the filtering circuit seen on one of the following slides. Briefly taking a look at the sensor power supply, the voltages are fully adjustable for each LED pair on the sensor, and the current is limited for each LED within specification limits to maintain longevity of the sensor. The lights can be switched on and off at high speeds on the order of microseconds, with the transistors being driven by the microprocessor, allowing for simultaneous monitoring of heart rate and pulse oximetry. All wires are color-coded, as are the voltage adjustment knobs, and the sensor itself was outfitted to a USB interface. This reduction was done to isolate the power supply from the filter breadboard to limit electromagnetic interference. The filter circuit is an array of 5 filters, not including the ferrite ring at the end of the circuit, which we'll get to later. In the upper left, the circuit can be seen assembled on a breadboard and was intentionally left larger and more spaced out than necessary to allow for proper troubleshooting and diagnosis. From the left side of the schematic, we can see the 6 Hz low-pass filter designed to filter out frequencies above 360 beats per minute, and this is just seen as the first resistor-capacitor pair. While this does seem like a high cutoff, this first filter is the first of multiple low-pass filters, which progressively step down to generate a Butterworth-style filter with a more abrupt cutoff than each filter independently. Second, there is a notch filter designed to attenuate 60 Hz electrical noise as seen in residential housing, and this filter would have to be adapted based on location of use, as military electrical runs on 400 Hz, and therefore military craft would require a 400 Hz notch filter. Following that is our 0.8 Hz high-pass filter, corresponding to a heart rate of 48 beats per minute on the low side. The fourth filter in the series is an active filter with an adjustable gain on the amp from 2.6 to 260, so that the very small signal can be brought up to a usable level. This active filter also brings the analog signal up to about 3 volts via the V reference positive pin, so that a good dynamic range can be seen from 0 to 5 volts. This active filter also contains the second 6 Hz low-pass filter of the array, causing the circuit to more aggressively cut out high-frequency noises like cell phone signals. Finally, a 4.5 Hz low-pass filter was added to further reduce high-frequency noise with a more reasonable max frequency of 270 beats per minute. And then the ferrite ring is the final filtering step, which uses the induction of eddy currents to numb the high-frequency peaks. The output signal can be seen for heart rate at the top of the page here, and 2 things can be noted. Amplitude varies, and the signal is inverted. The latter can be corrected for much more easily in a future version of the circuit with an inverting op-amp, and the amplitude variation is a matter of motion artifacts, i.e. the sensor moving on the forehead. This can be corrected for in a variety of ways, one of which could be an addition of a silicone rubber layer on the sensor to reduce motion of the sensor. The sensor output was compared over 6 10-second intervals to the gold standard, the Contact 50DL optical finger heart rate monitor, and the design sensor showed an output of 96 beats per minute, while the contact sensor showed a consistent 101 beats per minute, leading to an overall error of 4.9% or an accuracy of 95%. And unfortunately, due to an infrared LED burning out in testing, no data can be collected for pulse oximetry at this time.
Now, the next sensor developed by our team was the body temperature sensor. The target conditions for this temperature sensor were hypothermia and hyperthermia, in particular heat stroke versus heat exhaustion, which can be better distinguished in conjunction with our next sensor. The features of interest for the body temperature sensor are body temperature being measured as a resistance. This is done using a 10 kilo ohm NTC thermistor, which is wired in a voltage divider. In this voltage divider, a 33 kilo ohm known resistor is wired in parallel with the thermistor probe. An Arduino processor is then used to measure the voltage across the thermistor pathway, and using a temperature calibration curve created, this can then be related to a known temperature. Now, the biggest problem here, the biggest challenge, was selecting a correct known resistor that would allow the temperature readings to be within 0 to 50 degrees Celsius as desired by the client. The solution for this, a 33 kilo ohm known resistor, positioned the temperature voltage at approximately 2.5 volts at room temperature of 20 degrees Celsius, nearly in the midpoint, thus allowing for an accurate reading in the desired range of 0 to 50 degrees Celsius. Now, in the next slide here, a gold standard 6802 digital thermometer was used. Temperature testing here on the side can be seen for 3 trials conducted on 1-minute intervals for 20 minutes. Now, as you look here, you can see using standard deviation bars as well that there's no difference between the points. They're nearly all identical and overlapping. Now, looking at our p-value conducted using a t-test, we had a p-value of 0.33, and using an alpha value of 0.05 or a 95% confidence interval. This indicates that there's no statistical significance between the temperature probe or the gold standard, and a calculated percent error of 0.1% was calculated, thus giving a calculated overall accuracy of 99.9%. In addition to this temperature sensor, a perspiration sensor was conducted, and as hinted at before, a perspiration sensor could detect dehydration, heat stroke, and heat exhaustion. Heat stroke being a serious condition where sweat is no longer present, and heat exhaustion, a normal condition experienced by most people outside in hot conditions in which you're sweating to cool the body down. Now here the feature of interest is perspiration, which we're measuring again as a resistance this time. This is now done using 2 electrodes in a voltage divider circuit. So these 2 jumper wires here act as perspiration probes, which are attached to the user's skin to create a circuit. And then three 1 milliohm resistors are in parallel with these probes. Again, Arduino processors used now to measure the voltage across the perspiration probes this time, instead of over a temperature thermistor for the perspiration sensor. The biggest challenge here was setting a threshold voltage that would accurately indicate normal skin conductance as being non-sweating. And the solution to this was using a threshold of 4.83 volts to identify as normal skin conductivity and not sweating. Now moving on to our next slide here. On the left, you can see our perspiration simulator setup. This was used a saline solution. Inserting both probes into the saline solution was done to represent perspiration. Removing the probes from the solution then represented non-perspiration. Perspiration values were assigned a binary value of 1 for sweating or 0 for not sweating. And 3 trials were conducted over 20-minute intervals using a random number generator. And as you can see, nearly all sweating conditions were measured. In one trial, one more sweating condition was measured. This led to a overall sensor accuracy of 97.0% because of a percent error of 3.0%.
So respiration is important to monitor for several reasons. Not only could the information on breathing patterns indicate effects of poor cabin air quality, but it can also give information on other conditions that affect breathing, such as stress and unconsciousness. In order to gather useful information, we must be able to detect both the depth and the frequency of breath. In our research, we found that the most non-invasive method for doing this is to monitor respiration using sound, which is the method that doctors actually use by putting the stethoscope to your chest to check your lungs. To do this, we implemented a special microphone, the microphone which is attached directly to the microphone of the headset and is directly pointed towards the pilot's nose, as shown in this image to the right. A small challenge comes with using this method to detect respiration, and that is the fact that the sound of normal breathing is actually very quiet at 10 decibels. So in order to overcome this challenge, to distinguish the sound of exhalation from electrical noise, we 3D printed a case which acts as a funnel to funnel the sound towards the microphone, similar to a stethoscope. Here we can see a sample of data from the respirometer itself. In the standard practice, we count the number of breaths over a 15-second interval and multiply it by 4 to calculate breathing rate in breaths per minute. Here we can see the specific intervals that our algorithm is using to count those peaks in that 15-second interval. We also see where the program is able to detect a peak, and we are also able to get the amplitude and the frequency of the breath from this data. Amplitude being related to the depth of breath, and the peak frequency being related to wherever the program is detecting our peaks. Again, having these two pieces of information allows us to very easily determine the different modes of breathing. As demonstrated in this figure, we can see unique traces for normal breathing, hyperventilation, deep breathing, and there are many other kinds that we haven't tested, but these 3 in particular are very unique and things that we want to monitor. So a user could very easily look at this data and determine if a pilot's breathing is abnormal. To determine the accuracy of the device calculated rate was compared to breaths counted manually over the same 15-second interval, and this was done for a total of 5 minutes. The average rates were compared using a two-tailed t-test, as shown here. And as we can see, the statistical analysis of this data shows that there's no significance between the device and our manual method. So we are able to say that our device is capable of detecting respiration. Overall, this test was repeated 3 times, and the overall accuracy was determined to be 97.5%, which is well above the specification that we were required. Unconsciousness is something that pilots must worry about because of the G-forces they experience and the potential lack of oxygen due to the altitudes they're flying at. This is especially an issue for fighter pilots and stunt pilots, which may be flying more aggressively and experience rapid changes in acceleration, which can affect their neck and spine. The best way to gather this type of information is to place an accelerometer on the top of the pilot's headset, as shown in the image to the right. Information such as this can indicate exhaustion when the pilot is nodding off and their head is falling forward, or even stress when their head is moving erratically from left to right. To test the accuracy of the device, the accelerometer was dropped from a 5-foot height onto a soft surface, and the acceleration was recorded during this free fall, which was then compared to the known acceleration of gravity. The drop test was repeated 5 times, and the device recorded accelerations were averaged and determined to be 9.95, as shown in this table. Although a t-test showed that the average calculated by the device is statistically significant, the standard deviation and the point-by-point errors show that although the true value of acceleration is slightly off with our device, the device is precise to thousandths of a meter per second squared. The accuracy of the device is still pretty high with a 98.6% accuracy, and this issue can likely be resolved through the addition of a constant into our acquisition program.
So our central data acquisition unit is essentially the final part of our sensor suite design. The Raspberry Pi Model 3 was the chosen unit due to its relative low cost and its ability to handle the outputs from each sensor. As shown earlier, each sensor was designed around the use of Arduino nanoboards, which have high interoperability with the Raspberry Pi hardware via USB transmission. And so each sensor would be set up on a nanoboard and would transmit data outputs via USB to the Raspberry Pi central unit. The outputs from each sensor would then be routed through the Raspberry Pi for local SD storage, similar to the way that aircraft mechanical data is saved to a black box in the plane already. This would be an accompanying unit that could be recovered in the case of a crash, and that data then analyzed to get greater insight into what was going on with the pilot at the time. So data is saved in a CSV file format, which just allows for basic data analysis with the Pi itself, but then also for easier wireless data transmission, which would be something that would be added in the future. Because accurate timing is important for any data generated, timestamps were attached for each reading from the sensor data outputs. Part of our project, obviously, was actually building the unit. Unfortunately, due to COVID-19, we were unable to do so. Although we were unable to assemble it all together, the way we went about it, our continuity plan was to break out the sensors and work on them separately. So this did not allow us to go about our metric testing plan like we initially thought we would. So some of the things that we were unable to test specifically were additional flight prep time and headgear weight. These are both related to comfort for the pilot and I guess usability of the sensor suite. So something to be addressed at a later date if the project were continued. Additionally, we couldn't test all the sensors working in conjunction, so working all together, but we could test theoretical data streaming through the final data acquisition program and test the sensors individually to generate the accuracy data. And some technical errors and inaccessibility to extra components led to the failure for the pulse oximeter. Unfortunately, we weren't able to get final accuracy data for that, again, due to coronavirus complications. So for the specifications, the ones that we presented earlier, we compared the precision of each sensor to the gold standard that was mentioned, and then evaluated the difference between the initial accuracy and the final sensor accuracy. Our final accuracies for each sensor are actually much higher than we initially thought, which is a good thing. And we originally believed that the accuracy targets for the sensors should be scaled based on the relative importance of the sensor in the suite. So obviously heart rate monitor is kind of like the central sensor, so that one was a lot higher. But it actually turns out that this was unnecessary, as all of the sensors ended up having an accuracy of above 95%. So that's an encouraging result, and it's definitely helpful for the final headset sensor suite like product marketing, and we definitely achieved our goals in that regard.
Now, future work we would like to see applied to this project would be mounting all of the sensors to the David Clark H10-13.4 Aviation headset. This was the headset given to us by our client, which we were originally planning on mounting our sensors to. Along with this, we would like to see Bluetooth capabilities incorporated into the device. This would be done to eliminate a bulky wire harness, which could cause choking or entanglement of the pilot or crew members. We'd like to eliminate that. Along with this, we'd like to develop a antenna broadcast type system. This would allow for long-range transmission to ground crew members on the ground during search and rescue missions, which they could then monitor the pilot's health and safety at that time. And finally, we'd like to see an advanced algorithm created that would, instead of showing a general warning of just some sort of low temperature, possibly combining all sensors to then say whether it's a hypothermic condition or a shallow breathing, hyperventilation, some sort of better accuracy in characterizing these health conditions. This again would be on top of sending now the data to the ground crew members.
So with that, we just want to thank you for listening to our presentation. And we also want to give a personal thank you to our advisor, Dr. Michael Mason, and to our client, Dr. Robert Bowie. And with that, we're going to open it up to questions. Thank you.